So I think I'll just now give you sort of an overview or a summary of my views before going forward on this paper. So I think what they're saying is correct in that, yes, charge extraction won't extract all the charge carriers. This is well known. Sort of my biggest reservation about this whole paper is they completely neglect disorder, because these organic compounds are disordered. Like they are like spaghetti. You know, they're nothing like crystalline silicon, and they're nothing like sort of the 9 nines or 6 nines purity that you have for silicon. You know, I mean, if you look at the purity of these materials on the sort of the Sigma Aldrich website, they're sort of 99.9% on a good day. You know, they're not anywhere near silicon purity. So these materials are dirty and they are disordered, and this whole paper neglects disorder. So that sort of makes the theory that they present in this paper a bit problematic as we get further down it. And I also think you shouldn't be using charge extraction measure recombination for reasons I'll talk about later. So that's sort of the summary of what I'm going to say. So this is a new type of video that I thought I'd do, and it's a reaction video to papers that have recently published. So I think the concept is I'm going to drink a cup of tea or coffee, and I'm going to go through a recently published paper and just react to it off the cuff. So this is not sort of carefully prepared. This is just you know, a scientist, which is me, just reacting to a paper. So there's going to be sort of a bit of head scratching, a bit of reading, and thinking what they mean about what they write in these papers. And if you like this type of video, I will do it for other papers. So let's get going. The paper I want to look at today has been recently published, and it's called A New Framework for Understanding Recombination-Limited Charge Extraction in Disordered Semiconductors. And it's by Austin Kay and Oscar Sandberg. So let's have a little look where they're from. They are from Swansea. So most of the team's from Swansea. And Swansea is a very nice place in the south of Wales, which is in the UK. And if you've not been there, I highly recommend you go there. It's got beautiful beaches and it's a really lovely part of the world. The best to go on a sunny day. So let's get into this. Let's have a little bit of a read of the abstract. So recombination of free charge carriers is a key loss mechanism limiting the performance of organic semiconductor-based photovoltaic devices such as solar cells. So yes, they're saying that recombination is an important mechanism to describe charge carrier loss in organic solar cells. So this is the mechanism whereby a photogenerated electron and hole recombine in the device. The carrier density dependence of the rate of recombination and associated rate coefficients are often estimated using transient charge extraction experiments. These experiments, however, often neglect effective recombination during the transient extraction process. So it's when understanding solar cells, materials like silicon are very, very ordered. You can think of them sort of like a periodic lattice of like marbles in a tin. You know, they're very, 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 very structured materials, and some of the materials are incredibly pure. Some of these inorganic compounds are incredibly pure, and they come up to things like 6 nines or 9 nines purity, which means sort of 99.999999. I've probably lost count of nines purity, so like massively pure, and take huge amounts of energy to purify. Whereas organic materials like organic semiconductors and other disordered materials are effectively made of a sort of a mess of polymers that look a bit like spaghetti, so highly disordered. And you get because of that, you get lots of charge carrier trapping. So knowing how much charge is trapped is really important, because it enables you to understand the performance of the device. So charge extraction is used to measure effectively how much charge is trapped in these disordered devices. And the way it works, if you don't know, is charge extraction is effectively, in fact, there's a little picture of it down the paper, so I'll just skip this bit. The way it works is you run the solar cell at a certain voltage, say 1 volt or something, in the light. So the light's turned on, it's got a voltage, and all of a sudden you turn off the light and you turn the solar cell to short circuit. And when you short it over like a 50 ohm resistor or an ammeter or something like that, and all the current that was in the solar cell due to the light and the applied voltage suddenly flows out, and you can measure that over an ammeter, and you can figure out how much charge in your solar cell. And it's quite a nice technique to figure out how much charge in your device. And what they're saying is effectively this has been used to measure recombination in the device, which I find a bit weird because, like, usually charge extraction is used explicitly to measure the charge density in the device. It's not used to measure charge extraction. So that's a bit, I'm not sure. I wouldn't do that, but anyway, it doesn't matter. And it says these experiments, however, often neglect the effect of recombination during the transient extraction process. So what it's saying is that whilst you're extracting charge from the device, you're obviously going to have electrons and holes like recombining and being lost. And if you don't take into account of that, you might extract some of the charge that's in the device, but not all of it. I was saying that might lead to errors in your measurement. And yeah, I mean, I completely believe that. I mean, it's well been known for years, in fact, that you get carrier loss when you're doing a charge extraction experiment. So you've got all this charge in the device, and you're trying to get it out. It's not going to just move out perfectly. It will sort of, there'll be some loss on the way. And in fact, in the earlier charge extraction experiments, people used to measure the recombination rate using transient photovoltage, and then correct the charge extraction signal iteratively using the known recombination rates. But okay, so I think I'll just now give you sort of an overview or a summary of my views before going forward on this paper. So I think what they're saying is correct in that, yes, charge extraction won't extract all the charge carriers. This is well known. Sort of my biggest reservation about this whole paper is they completely neglect disorder, because these organic compounds are disordered. Like, they are like spaghetti. They're nothing like crystalline silicon, and they're nothing like sort of the 9 nines or 6 nines purity that you have for silicon. I mean, if you look at the purity of these materials on the sort of the Sigma Aldrich website, they're sort of 99.9% on a good day. They're not anywhere near silicon purity. So these materials are dirty and they are disordered, and this whole paper neglects disorder. So that sort of makes the theory that they present in this paper a bit problematic as we get further down it. And I also think you shouldn't be using charge extraction measure recombination for reasons I'll talk about later. So that's sort of the summary of what I'm going to say in a minute. But nevertheless, let's get into it. So, photovoltaic devices based on next generation solution organic process. So this is all blah blah abstract. So 19% efficiency, blah blah blah. It is generally expected that recombination rate in OPV is bimolecular of the form this, ideally characterised by carrier independent recombination. So this is problematic off the bat. This is not true. It is generally expected that recombination rate in OPV is bimolecular of this form. This is absolutely not true. I would not write that in the paper because it's so much more complicated than that, and it's absolutely not expected. This would be true in a highly pure material where you have free electrons and free holes zipping around like that. In disordered materials, I think they've even got disordered in the abstract. Disordered semiconductors, right? Disordered materials. You're going to have a lot of trap carriers. So rather than the sort of bimolecular free electron moving around a free hole, you're going to have one carrier trapped in sort of a deep. If I move back around, one carrier trapped in sort of a deep trap. The other one sort of freely moving around like this. And eventually, at some point, it's going to drop down to energetic level and recombine with it. And that's a very different mechanism to this bimolecular recombination. And also because all these sort of different, in a disordered material, because all these different carriers at sort of different depths, there's no reason why this beta should be constant. So this sentence is problematic, and it's just, yeah, it shouldn't be there. So, and it should be much more like careful on how it's presented, because I find this could be confusing for other readers. So despite this, charge extraction experiments have frequently suggested carrier densities of beta that leads to. Yes, okay. Let's continue. Let's leave that for now. Being attributed to recombination via trap-like states. So they're effectively saying changes in delta and change in beta have come from charge extraction experiments. Well, there's been a lot of different measurements done on these devices. I don't think it's just from charge extraction. It was recently shown, however, that most electrical techniques, including charge extraction, are detrimentally affected by capacitive effects, limiting the use at low illumination intensities. I mean, the common thing you do, so I'll look at those papers in a minute, but the common thing you do with charge extraction, you just subtract off the capacitive values. So when you do charge extraction, there's two parts of the current that come out of your solar cell. There's the charge that's sort of on the contacts of the device. It's just like any old capacitor, it's just like charge. And then you've got the charge in your device itself. That is effectively the charge that's sort of the free carriers that have just been generated, not yet been extracted. It's sort of the actual charge in the electrical semiconductor. So if you want to find the charge in an electrical semiconductor, you just literally apply the formula of capacitance, Q equals VC, and you just subtract that off from the charge extraction. So, not sure. Let's look at these papers. 9. That's the Nelson one. So I think that's a comment on TPV, that paper, and I don't want to go into that now because I've not got it up, and I'm not going to get it up because otherwise my cup of tea is going to be finished before we finish this video. But I think that doesn't have trap states in it, and I think that's a comment on TPV rather than TPC. So not sure about that reference there. 21 to 23. That's by these authors, so let's not look at that. That's another Nelson one. Mobility and item. I've not read that one. Capacitive concern. I'm not going to dig into those in detail now. But okay. Additionally, high intensity such as those characteristic solar fluxes on thin film diodes on low materials are affected. So basically, it's saying the measurements can be affected by RC time constants. How these effects influence determine beta and delta is not known. What I would personally say that capacitive stuff can be probably done with the back of the envelope calculation and a bit of care, and it is, yeah, it's sort of, I think quite a lot of this can be subtracted off. But anyway, fine. In this work, we investigate the validity of charge extraction to probe carrier density and the evidence of charge carrier recombination OPV. Specifically, we clarify the role of RC time constant and beta and delta, indeed utilising open source drift fusion model presenting supplementary information. Now, I've had a look at this model in the supplementary information, and my biggest issue with it is there are no trap states. And I made a video on trap states before, but like we are dealing with here, it says a disordered semiconductor. It says disordered semiconductors, and you can't model disordered semiconductors without trap states. You just can't do it. It's wrong. So any comparisons with modelling that goes like forward has got to be treated in that context that the model isn't really made for disordered semiconductors. So just like to put this really, really clearly for the community, you can't use standard drift diffusion models for disordered semiconductors. You need to include trap states properly, and if you don't, your results are going to be wrong. So, yeah. Anyway, let's keep going. And series of resistance. Okay, to overcome these limitations, we provide an analytical framework through which charge extraction measurements may be interpreted. Okay, fine. So, right. So this is their diagram. This is actually quite okay. So they've got some light coming in here. There's your capacitance on the cells, so that represents the contacts of the device. This represents the semiconductor itself, a bit of series resistance, a bit of shunt resistance, and that's their load resistance that's effectively simulating them sort of plugging in the ammeter to their device to short it out. So I'm not going to go through that. Just a little bit of tea. Okay, so a bit of an equation there, all good. Now then, here we are back to this bimolecular recombination. Assuming uniform charge carrier distributions, these conditions relate to this. Now, as I said above, this is problematic because they're assuming effectively it's bimolecular recombination, which means like no trap states, which is not really okay if we're dealing with disordered semiconductors. So, like, but what they do have here, which I'll give them credit for, is having beta NOC. So, effectively, they're saying in this equation up here, they're just saying, where has it gone? They're saying effectively recombination is a function of beta times n squared, which is like you've got one electron, you've got another hole, you've got two of them, therefore the probability is one times the other, so that's the n times a fixed beta. But what they've done here is they've made the beta carrier density dependent, which is like more correct and more supported by the experimental evidence. Okay, then we go up here, and they're effectively saying at VOC, so no, actually they'll probably say it down here, actually, don't they? They say it down here, but we'll come back up to this. They're basically saying at VOC, the recombination is equal to the optical generation. So this makes sense because if you imagine your solar cell like just sat there and you've got photons coming into it like that, the photons are going to generate electron holes, and these electron holes, if your solar cell is not connected to anything, so at VOC, it's just like sat there on the desk, they can't like build up infinitely. At some point they've got to start recombining with each other, and you're going to sort of have this equilibrium form between generation and recombination. You can't have like an infinite build-up of electrons and holes in your device just because you shine light at it. It's just not physical. So at some point, the recombination rate will equal the generation rate. So you have this sort of steady state. So this is correct. And then what they do is they effectively say that, okay, at VOC or at sort of I guess at steady state, you've got you can effectively rearrange this equation down here in that you can get this NCE from integrating this. So you can get the charge in your solar cell from integrating this. And how do we get the recombination rate? Well, at open circuit, the recombination must be equal to the generation for the reasons I just said. So if we can just measure this, which you just measure how much light's coming into your cell, you've got the recombination rate. So you can get recombination rate divided by NCE equals beta. And then you can get your NCE. Then you can get your beta. So effectively what you've got here by rearranging this equation and running it at VOC is you've got a way to get a beta, which is quite useful to understand how charges recombine in the cell. And here, this maths that we skipped, this is what I was talking about earlier, effectively. So what this is this is the integral of this transient here. So that's just all the charge you've extracted from your solar cell. And subtracting off it QV, which is the charge on the plates of the device. So that's just capacitive charge. So effectively, NC is the electronic charge in the solar cell. This is effectively like the electronic charge, because obviously capacitive charge doesn't have any influence on like what's going on inside the device in terms of recombination. So that's just mathematics of what I said previously. Okay. Now, so here they say, here B determines the recombination. Yes, right. Either can be yes. I said this. Am I going to pick up on this? So they say G light, noting that via the saturated photocurrent density G. So they're also saying not only can do this at VOC, you can also get a measure for this this G light by reverse biasing your solar cell with a large negative voltage, and looking at the reverse bias current you get, so basically JSC, but a bit further negative. I wouldn't do that, because you would still have some recombination there, I reckon. You know, possibly some geminate recombination, or some. I don't think you'll get rid of all recombination just by going to negative voltages. So this I believe, this I don't. So that's my feeling on that. Or in conjunction with transient photovoltage measurements. Now, this is very different, right? So all this relies on effectively doing just charge extraction. And the thing with charge extraction is it's a very large signal measurement. So you can think of TPC like a bathtub. So you can think of the solar cell. You can think of the solar cell as a bathtub, and it's full of water, and the water's a charge. And then all of a sudden, you pull out the bath plug, and all the water goes straight out the bottom. So that's effectively charge extraction, and it's a large signal measurement. It effectively destroys any equilibrium processes that are going on in the solar cell. So at equilibrium, there'll be like a charge distribution, there'll be recombination happening in different places, everything will be sort of in equilibrium. And charge extraction just wrecks all that, because it like destroys where all the charge in the device, just rips it out, and it moves the device to a very, very different and new state. It's not really made to measure recombination. To measure recombination, you really want measurement techniques like TPV, like impedance, photomodulated impedance. I can't remember the words. IMVS, things like impedance spectroscopy. You want sort of very small signal laser measurements that don't really move the solar cell out of its equilibrium state, because as soon as you change the light or the voltage a lot, all the recombination rates and charge profiles are going to change. So you want some type of measurement when you measure recombination that just sort of perturbs what's going on in the cell just a bit, so you can measure it. And the way TPV does this is it just shines a laser, very, very small laser pulse, and just perturbs the voltage at VOC. Just a bit, you just measure that transient, and you relate that to what's going on in terms of recombination. So we really here got two different, very, very different approaches. We've got the large signal where you're ripping the bath plug out of the bath to measure the charge and hoping you get some information about what's going on with recombination. And then they're talking about TPV, which is like a very, very small perturbation technique that sort of just measures the bath level like very, very carefully without changing it too much. So those are quite different regimes, and personally I wouldn't expect charge extraction to be able to measure recombination, just because of how much it perturbs the steady state, whereas other small signal techniques I would expect to be able to do it. So okay, so I think you've got to be a bit careful about how we interpret this. Equation 4 allows for the detection of any carrier densities dependence of I just don't think it does. The equation 4 allows for the detection of any carrier dependence of BCE. It doesn't, but for the reason I just explained, is that you're effectively you're trying to measure a delicate system, and you're just like ripping the bath plug out of it and totally perturbing it. So you can't just use charge extraction to get that. I think with TPV you can, and people like the Durrance group with sort of JV reconstructions and stuff they did years ago, they showed it works. So yeah, okay. However, equation 4 relies, I'm going to be a bit bogged down here, we haven't really got to the interesting bits, but anyway. However, equation 4 relies on the assumption of uniform carrier density prior to T0 and complete charge extraction after T0. There's a lot to unpack there. Equation 4 relies a lot more than that. It relies on neglecting trap states, no disorder, bimolecular recombination. What else does it rely on? Probably lots of other things I forgot to mention, but relies on the assumption of uniform carrier distributions. I wouldn't really say that the uniform carrier distributions were the problem. I wouldn't really say they were a problem when you've got all these other things going on. I'd say they're like a second or third order problem when you compare it to all these other things. The form is generally violated at low intensities by the manifestation of capacitor limited regime. I'm not sure. I'm not going to find out what the former is. I can't be bothered. The validity of the latter is expected to depend on electron hole mobilities, respectively. Yes. Okay. I'll come back to that later, but whatever. For materials with low carrier mobility like OPVs, the time it takes to extract all the carriers may depend on the carrier density and be longer than the prevailing recombination lifetime. Right, so this is, okay, now I'm starting, there's a few other things that are raising their head here. So they've got mu and n, so they're talking about mobility in OPV devices, but the problem is, in OPV devices, you've got effectively an ensemble of carriers in a distribution of trap states, and because of this, you don't have you don't have a single mobility. So I'm just going to try and explain this with a picture. I'm just so this is unprepared, right? So this here is a paper that I wrote a long time ago, and you can probably, shall I show you the DOI in case you want to read it? There's a DOI in case you want to pull this off the internet, but I'm not going to the cover page. So this is a picture, a diagram of the distribution of states in a disordered material, like what we're talking about here, disordered semiconductors, right? So you've got effectively trapped carriers. So these represent trap carrier states. These, and this is just a cartoon, a bit more complicated in real life. And these represent trapped carriers, these triangles. So there's carriers trapped down here, and there's free carriers up here. So this is free holes, free electrons, trapped electrons, free holes, trapped holes. Okay, and you sort of have a distribution of carriers. So the higher energy ones are free, the lower energy ones are very trapped. As you get sort of higher and higher up in energy, the carriers spend more time being free than they spend being trapped. The deeper down you get, the more time they spend being trapped than free. So you have this sort of this energetic ensemble of carriers. Now, if we think about that in terms of mobility, so just sort of keep that picture in your head. So I'm just going to get a different picture up. So what have we got here? Is that one? Yeah. So if we think about this in terms of mobility, so here's a this is another recent paper that you can pull the DOIs out, but I'm not going to sort of push my papers, as it were, because I don't think this is the forum for that. But if you think about this cartoon in combination with this equation, so this equation is basically saying this is the average mobility in semiconductors. So imagine we've got like it's disappeared, isn't it? Imagine we've got a free carrier mobility. So all these carriers up here are free, and they've got a mobility. They can move around like a ping pong ball with a mobility. And we've got a number of free carriers, so that's all the free carriers here. We've got a number. We're just talking about electrons at the moment. We've got a number of free carriers, a number of trap carriers, right? So imagine all the carriers are free. So this is a very big number, and that's 0. So we've got a big number divided by a big number, which is 1 times mu free. So effectively, we've got an average mobility of mu free. What makes sense? All the carriers are here, energetically moving around. So we've got an average mobility of mu free. Okay. Now think about the opposite scenario. All the carriers like deep down in the trap state, so they're all like down these tails. We've got no free carriers, that's 0 times free mobility. Well, 0, and then we're going to divide it by a big number because all the carriers are trapped. So we've got 0 times mobility is 0. So our average mobility is 0. So in the two extremes, we've got all the carriers are free, average mobility is mu free. All the carriers are trapped, mobility is 0. And in reality, if you're at like room temperature, you're going to be somewhere in between that. You're going to sort of have a happy medium of some carriers trapped, some free, and you have sort of an average. So it's usually about an order of magnitude lower than mu free. So keeping that argument in mind and moving back to this argument, they're starting to talk about mu n and mu p as like values, but they're not just like values. It depends on the condition of the device in. You know, if there's a lot of carriers, if it's cold, if it's hot, all the distributions will change and mobilities will change. So you can't talk about a mobility in OPV devices. This is just wrong. And this is because, and the reason they're making this mistake is because they're neglecting disorder, and which you can't do in a paper about disordered semiconductors. So this is like difficult. I'm finding this quite difficult. Okay, so to clarify, but okay, we take their point that yes, if the mobilities are low, it will take time for the carriers to get out and they may recombine. But I would also point out, if you redo these simulations with trap states, it won't be the low mobilities it's affecting, it'll be the carriers get trapped, and that's the reason why they take a long time to get the device. So I think they should be using a model with trap states. I really do. I really think as a community we should not be simulating like like disordered semiconductors with models that do not have trap states, because there's people have been modelling disordered semiconductors since the 60s or whenever it was with all amorphous silicon, and they all knew about trap states. So why we should be ignoring it now, I just do not know. Okay, right, moving on. To clarify this, so that was a rant over. I think I'll just have to take a sip of my tea. So to clarify the influence of carrier mobility on extracted carrier densities, several light intensity dependent, i.e. carrier dependent charge extraction was simulated using drift diffusion model. Well, this is a problem because you can't do a simulation with a mobility in a disordered device, because I'll just explain the mobility changes, as a function of the carrier density, as a function of temperature, as a dependence of light. Because, as you so things that will change distribution carriers in this distribution. If you imagine ramming it full of electrons, the Pauli exclusion principle is going to mean you're going to get more free carriers sort of in the free region. If you remove the number of electrons, you're going to be taking them out of the free carrier states first. If you reduce temperature, they're all going to sink down to the bottom. If you increase temperature, they're all going to go up to the top. If you do a lot of photogeneration, you'll have a lot of free carriers zipping around here. So the whole dynamics of this thing that determines mobility will depend very much on the state that this thing is. So do the simulation with a mobility is wrong, or at least in my view, it's wrong. Okay, so then we move on to some results. So should we move down here? So recombination coefficient was fixed at beta 1.2 times 10 to the minus 11. Now, I work in meters usually, and that's to the minus 17, and that seems high to me. I've looked through the SI, I won't do it now, but I can't find a JV curve for this device they're simulating. And I suspect if I simulated a device with that beta, I don't think it'd be a great device. My guess is it's going to be like a sort of a 3% device. I might be wrong, I've not done the simulation, but it would be nice to see a JV curve, because obviously if the device has got loads of recombination, of course a lot of the charge is going to get recombined before the charge extraction gets a charge out. But if it's got a low recombination, then this whole paper's mute, which I don't think it is, by the way. I don't think this paper's completely mute. I just think I'd like to see a JV curve for that. Corresponds to the case for bimolecular recombination, and we already talked about that. That's a bit of an assumption there, so let's say it mildly. For all results presented at this ohmic context, that's fine. Figure 2, it is evidence that NC depends on mobility. So figure 2a. What is figure 2a? Well, there's the charge you extract from the device, and there's the lights, the generator light. So this effectively, they run the experiment at various light intensities, and they see how much charge it got out. But I'm not saying these results are not correct, but the problem is they've just got free charges and they've neglected disorder, and a lot of the charge is going to be in the trap states. So this graph is like suspect. How this would be when you have charge carrier traps, I don't know, but they've not done it, so I don't know. But this doesn't really make sense for a disordered semiconductor. It says in the title disordered, and there's no disorder, so I don't know. Okay, so here we go. Recombination rate constant against NC. Well, I've sort of already made the argument about, charge extraction is a large signal technique, and I probably wouldn't use it to measure recombination. It's probably brilliant for measuring carrier density, and you can go back and correct the charge extraction with the measured recombination rates from something like TPV, but I wouldn't expect that to be right. So anyway, whatever. To verify the apparent variation with increasing carrier density, an artifact. So they're basically trying to prove that charge extraction can't measure BCE, which I think it probably can't, and I probably wouldn't use it for that. Okay, let's read more. To verify that the apparent variation. To simplify the treatment, we assume the photoactive layer is sufficiently thin, okay, and light generation is intense enough for photogenetic electron hole density profiles to be flat across the entire layer. in the steady state prior to charge extraction. I mean, if it's a really thin device, the generation is going to be sort of flat. With ohmic contacts, well, I guess if you've got quite strong light, if you've got a strong light, probably that's true. That's probably true. Such capacitive effects can be neglected. Now, capacitive effects basically means this capacitor here. Now, if you're in steady state, you can neglect the capacitor, it doesn't matter at all. But if you do any type of transient stuff, you've got one dynamic component here and another dynamic component here, and they're effectively both fighting each other. So you've got charge in here and charge in here, and they're both like you know, because you imagine if this drains of charge, you'll get filled up by the capacitor. If this changes of charge, you'll get filled up by that. So you've got sort of two differential equations fighting each other there. So you cannot neglect RC effects in time domain. You just can't do it. Not even in slow stuff like C-lift transients. You just can't do it because it's like a key feature of C-lift transients. But anyway, I'm digressing. Under these circumstances, the carrier density can be approximated and equal in accordance with equation 2. We expect that. Well, that's wrong because for a disordered material, this is wrong for a disordered material because you're not taking into account trap states. You're not taking into account this entire ensemble of complex processes that are going on. So this is, you know, that might be right for gallium arsenide or something like that, but unlikely for disordered materials, really unlikely. Immediately after the light and applied voltage have been turned off, the sudden change in bias conditions causes the photoenergy to start drifting under the influence of electric field. Yes. In the case of negligible series resistance, well, for my experience, series resistance is not usually negligible. It's usually a few ohms. So okay, but whatever. The corresponding magnitude of the electric field may be approximated as yes, neglecting diffuse effect electrons are extracted as that moving out of the active layer in a uniform sheet, leaving electron depleted region. This seems very familiar. This is sounding a lot like C-lift to me. At the same time, holes drift drift as a uniform sheet. Right, so this is all C-lift theory. This is straight C-lift theory. So let's have a look at C-lift theory. So here we are, I prepared one earlier. So lucky for me, in 2013 I was organised enough to already have been prepared. Well, I've done my homework for this paper and I have published this. So this is what they're describing in cartoon form. They're effectively saying, right, we've got free electrons and free holes, and when we apply our charge extraction, so when we short our device, now I'm only going to talk about electrons in this picture. Well, this cartoon only talks about electrons because that's all I was talking about here, but they're assuming the same happens for electrons and holes. But basically you've got free electrons here, free holes here, and when they short their device, they effectively shift in a sheet these free electrons out of the device, and they're progressive. It's like sliding sort of, I don't know what it's like sliding. It's like, I don't know, marbles rolling down a ball or something. Just like roll them out of the device. So effectively rolling the electrons out of the device there. And the same would happen to the holes. That's what they're saying. So that's their theory. However, in a device with disorder, so like this with disorder, you don't get that. What you actually get is you get when you short it, carriers in the least trap states detrap first. So the shallow states detrap first, then the deeper trap states detrap then, and then the deeper trap, and then deeper and deeper and deeper and deeper. So you're not just sliding carriers out of the device, you're detrapping at deeper and deeper and deeper and deeper energy levels. So it's not just a sliding, it's like a detrapping. And that's what's shown here in this picture. So effectively, we detrap and move the electrons in shallow traps out first. Then we detrap the electrons in lower traps for that next, and then we detrap the electrons in deeper traps. The same happens with holes. So you sort of get this energetically depth-dependent detrapping and removing of carriers from the device, rather than just like a sliding out. So, and that's in a disordered device. So this all sort of applies. It's sort of applies in a oops daisy. This sort of applies in a in an ordered device, but for a disordered device, this is like not really what happens. So that lays issues for the next theory that comes up now. Now, this equation, again, presents problems because they've got a constant, they're effectively saying we're defining some ratio that fits in with our theory called TR, and we've got a constant electron mobility and a constant hole mobility. Well, we don't have a constant electron and constant hole mobility because we've got this sort of dynamic of carriers, as the distribution of carriers is changing our device as we're performing an experiment. So here, actually, on the same paper, here's an example in the C-Liv. So if you do the maths, so this is a C-Liv transient. So a C-Liv transient looks like this. You effectively just apply a ramp of a negative voltage. It's a bit like the charge extraction, but a bit slower because the charge extraction just shorts out, and this is a ramp. And as you apply this voltage ramp, the mobility in the device and all the carriers get drawn out here. So this is the C-Liv transient. They all get drawn out there like that. As you do that, you're ripping out all these carriers, and the mobility is decreasing the device, the reason we talked about before. And you actually see a drop off in mobility by like an order of magnitude, just because you're ripping out the carriers. So your mobility is changing during your measurement, and it will depend on the voltage ramp you use and the conditions you're in. So this is very, very variable. So to have a constant mu n and constant mu p is just like, again, neglecting disorder, which is not right for a paper about disordered materials. And then, okay, device screening length, bimolecular, okay, fine. And then we do some maths. Now, I've not dug into the maths in the SI. I just, it's just too much to do. And my tea's already cold. But, this beta won't be constant because it's not, because it's a function of charge carrier density. This TR won't be constant because the reason we talked about with mobility, like there's a lot of evidence in literature for beta being carrier dependent. There's a lot of evidence for mobility being carrier dependent, so you can't just neglect this. So this equation, if you assume those, like, doesn't really hold. And the same with all these, because you can't just have a value of TR because it changes during the experiment. So in my view, like I've not dug through it, but in my view, the initial parts of derivation are not really right for disordered materials. That I suspect makes all these equations not quite so right too. And then they talk about their model, and I've had a look at the model, and there's no traps in it that I can see. It's just a straight up drift diffusion model, which is not valid for disordered materials. And then at the bottom, they somehow say the effects can be corrected if they assume R equals 1,000 ohms. I don't know why they said that's a bit weird. So overall view of this paper is that it's a paper on disordered materials where they've neglected disorder. So, like, we shouldn't do that as a community. The model doesn't have disorder in it. We also shouldn't do that as a community. What else? I think the concept that charge extraction loses charge as you extract it is correct. I think we've known about this for a while because people like Durrant, I know, were doing iterative correction to charge extraction using TPV data like 10 years ago. I do not think we should be using charge extraction to measure recombination. I mean, you can, but it seems a bit suspect to me. And then sort of making all these assumptions about bimolecular recombination, which might not hold when we've got traps, or won't hold when we've got traps, is also a bit suspect. So overall, are they right? You can't really use charge extraction to measure recombination. Yes. I find it difficult though that we're making, like, in the beginning they say, despite this, charge extraction potential be frequently suggested a beta dependence, and this is bigger than 2, and attributed trap states. Like, I don't think charge extraction experiments alone have been attributed to that. There's a lot of other evidence in literature. Like, there's a lot of other evidence in literature for this. So I think you can't use the fact that charge extraction doesn't work when you use it alone to measure recombination to sort of point that delta and beta don't change. That's what I think, if that's what they're getting at. So let's have a read of the conclusion. In conclusion, we developed a simple analytical model to describe charge extraction. By applying this model to drift fusion and experimental data, we have shown that the bimolecular recombination of excess charge during the transient extraction process of charge extraction generally leads to incomplete CE in diode devices with OPV. Well, I guess it depends on your recombination rate. With low carrier mobilities, we talked about mobility before. This in turn may result in erroneous evaluation of bimolecular recombination rate, but I think lots of people use lots of different measurements to get at to change the beta and delta. Lots of frequency domain stuff. So constant and overestimation of recombination on low mobility diodes. We can't talk about the concept of low mobility. We talk about variable mobility. To overcome these underlying limitations of C experiment, we have presented a new framework which just doesn't, in my mind, doesn't hold if you haven't got traps in there. So we've demonstrated how this model can be applied to correcting. If the model has not got traps in, I don't see how it can work. So I think you've got my view of the paper. I mean, yeah, I wish they'd put traps in it. I think that's the bottom line, and I wish they thought about that whilst doing the paper. So that's it. I hope you enjoyed that little video. If you like this type of format, I'll happily do more videos. Just just like the video and subscribe to my channel, obviously, and put papers you'd like me to go through in the comments below. And if there's something in my field that I think you'd like me to take a look at, I'm happy to. I'm not very interested in doing OPV. I'm not very interested in doing perovskite devices because, I'm just not interested in perovskites. There's too much lead there for me to be interested in them at all. But OPV stuff, happy to have a look at. So drop it in the comments below. I'll happy to take a look. So that's it from me. I hope you have a great weekend, and see you soon. Goodbye.